Thank you, Professor May, and thank you for inviting me and talking on this platform. And because I've been working for the last 2 decades in the Ladakh sector, so I thought, it would be nice to give an overall view of the climatic and the tectonic interplay of that region, which is which is the basis of all the disasters that are happening and that have happened in the past in that region. So because this is a lecture series on the collaborative Indo-German project on estimating and predicting natural hazards in the Himalaya. So in this talk, I've done it in such a way that, I'll be giving an overview of what was happening in the past as far as sediment records are concerned, and which is, an alarm for the future that we need to think on those lines. So formulated my talk as because Himalaya and Ladakh, this part is it comes under the third pole. So we'll a few slides on this third pole, and about the Himalaya, Northwest Himalaya, Ladakh, and then why Ladakh? What is the importance of this area as a whole, and then a few slides on the archives and the proxies that me and my group has been using. We'll talk more on the paleolake sediments that are all along the valley in this region, and then the glacial lakes which are on the mountain ridges, that is especially the Ladakh range, and then a kind of review of all the things. So when we see the distribution of the arid deserts in the world, what we see is when we see it in reference to India, so India, we have a hot arid desert also, and we have a cold arid desert also. And today we would be, going in the next 40-45 minutes, I'll be taking you to this area, which is, the northernmost part of India, towards the northwest. It is a cold arid desert. The altitudes here are above 3,000 meters above sea level. It has very, very sparse vegetation because it's above the tree line, and it witnesses extremes of temperature as all deserts do. And because of that, it has intense physical weathering because of frost action, and there are pronounced neotectonic signatures that we see in the sediment record here. So, and all this comes under in the third pole region, and we all know that third pole is a massive region with the Hindu Kush and the Tibetan Plateau and the entire Himalayan range. It is very important. It's known as the water tower of Asia. Very important because it's feeding like 20% of the world's population, and it is a ecological hotspot, and it caters to a huge population. So this is Ladakh. This is the map of Ladakh, and you see this river is Indus, which is the backbone of the entire area. So if I from the Himalaya, from the plains, if I just take a transect like this, because we all know, we all are here Himalayan workers here, we all know we have a Himalayan frontal fall, MCT, and Sucha zone, and the Karakoram thrust. If I just take a transect like this, we have the outer Himalayas, the lesser Himalayas, higher Himalayas, then a thick pack of the Tethyan Himalayan sediments, and then we come to the Trans-Himalaya. So Indus is, as I said, is the backbone here, and it has several rivers, tributaries like the Shyok. Shyok is one of the major right bank tributaries of Indus, and several, the fifth and the fourth and the third order streams that directly they come to the river Indus. So we are talking of altitudes at around 3,000 to 7,000 meters above sea level. This area is very important because this particular area where we are into. So this has been a part of the ancient silk routes, which were a connect to of the East Asia to the European countries. So not the main branch, but the sub routes used to pass in this areas. And in our climatic record, we do see the signatures of that. Then as far as sediment is concerned, so it has a huge sediment diversity. We have, there are slopes, they are blanketed with these debris, and then we have aeolian deposits as in forms of sand dunes and sand ramps. We have lots of paleoclimatic, paleolithic signatures. This is, the famous Moonland or Lama Yuru Formation. You can see the beautiful shoreline preserved here. Then we have a lot of, the permafrost is there, and there is an interplay of the fluvial and the lacustrine sediment species. As far as ecological diversity is seen, you can see, the glacial lakes where everything is frozen, and you can study the psychophiles, you can study the thermophiles in the hot springs of this region, and also the halophiles in the saline lakes which are there. This is Sokar Lake. Yeah. So owing to its climate and its location, it is a very important region, as it forms the environmental boundary between the North Atlantic monsoon forcings that majorly affect this area, and the rest of India is, it's more Indian summer monsoon dominant. But in case of an intense Indian summer monsoon, the monsoon, it penetrates into this region, and you can see this interplay. And in the geological record, in the late Quaternary, you can see these fluctuations or these periodicities when these forcings have changed over time. So being situated in this area, it is able to attest the slightest change in the dynamics of these two components, and also characterize signatures of these weather systems in the sedimentary archives. So this is the area again, a little closer look now. So what is, as I said, Indus River is flowing like this. It flows up along the Indus-Ucha zone. Another tributary, which is the Shyok River, which comes from one of the tongues of the Siachen Glacier. Siachen Glacier is the longest glacier outside the poles, terrestrial, in a terrestrial setting, in a continental setting. So Remo Glacier, the Shyok comes, it takes a U-turn, it is joined by Nubra River, and they both flow, and they join the Indus at Skardu, which is in Pakistan. So what we would be going is in this area and in this area of the Indus River, and we will be seeing our results. As far as geology in this area is concerned, we all know that Indus is flowing along this Sucha zone, and where on the northern side is the Ladakh batholith, and the southern side is the Indus molassic sediments, and then the Tethan Himalayan sediments. And they are several. The Karakoram fault is here, the Ashok Sucha zone is here, and Indus Sucha zone is there here, in which show some kind of a neotectonic signatures even during the late Quaternary. As far as the geomorphic landforms are seen, we see that they all are like glacially driven. We have wide valleys which are alternating with some deep gorges. We have gradational terraces, there are fill terraces, that's strut terraces. We see deflected stream courses, sometimes, the fan to cutting by the river, and then there are abandoned channels that we see. There are some fluvially modified alluvial fans. There are many signatures which are showing reworking, which are a result of reworking, or the fluvial incisions are seen, the valley fill deposits, the lake facies, several debris cones, scree, talus. It is a beautiful sight to observe all these geomorphic landforms that one can imagine in a glacial and a fluvial kind of topography. Basically, the overall geomorphological evolution is governed by two sets of geological processes. One, we all know that it's the continental scale geological processes, that is the Himalayan orogeny that has already, done a base of that area. And the second is this regional or the local scale geological processes, in which the role of tectonics and the role of climate is very, very significant in determining the glacial, the fluvial, the lacustrine, and the aeolian processes. So the archives that we were looking at, as I already said, that it is the terrestrial sedimentary deposit, where the climatic changes, the tectonic processes, and the surface processes we have been trying to, monitor this. by field observations, by geomorphology, by morphometrics indices, and also for high-resolution climatic data, which we were able to do in a centennial scale for the paleolakes and the sub-century scale for the glacial lakes. We used a suite of physical, chemical, and biotic proxies, and they were the chronology was radiocarbon AMS chronologies and OSL chronologies, in these sections. So we chose the lakes because we all know that lakes are dynamic systems that integrate environmental, climatic, and tectonic forcings into the continuous high-resolution archives for local and regional scale. And in Ladakh, we have multiple kinds of lake. We have these big open lakes like the Pangong. So we have the closed catchment lakes like the Sokar, which is, of course, a wetland now, but still it's a closed catchment lake. We have the Somarari, and these are like, kilometers wide. And then we have these paleolake sediments, as I showed you here, beautiful paleolake sediments. And we also, in the ridges high up in the ranges, we have these moraine dammed lakes or the proglacial lakes in a glacial kind of setting. So we targeted these for our study. First, I'll come to the valley. Yeah. So we'll go down the Indus Valley. This is Indus. It originates from the Kailash Manso River area, and it flows from Tibet and it enters India. And in India, the headwaters, it flows for about 442 kilometers. And what has happened is, in its course, Indus is sometimes, it shows a nice U-shaped valley, with valley to valley thickness is in kilometers. And sometimes it just follows it runs across these, through these gorges, which are very, very narrow and very, and for long distances. And that has been seen all throughout. And then what we see that wherever the Indus has a narrow, flow, the sediments of their paleolakes have been formed in the past. Yeah, so we will see how. So, here you can see the river Indus. It's flowing like this. And if you just see these buff color facies on both sides, these are massive clays and sills. So what we did was along the length of the river Indus, we tried to see this. We mapped only those which were more than 10 meters in thickness. Yeah, we wanted to do that. So from this area, we're just running down here, and I'll show how these paleolake deposits are. So you need not confuse with the names. This is like 27 to 30 meters thick deposit. There is another one. There is another in Sispol, in Rizong, in Khalsi, and so on. So they're all along the river. You see this, and they are. At some portions they have been already eroded, but in some portions where there are spurs and all, they are there where we could sample them. A detailed lithology and chronology was done, and what I want you to note is the chronologies are like 17,000, 15,000, 10,000, 3,000, 10, 6. So everything after the LGM, last glacial maxima, all along. Yeah. So what we did was we took a few paleolake deposits and few glacial lake deposits, because paleolakes were giving us a record till 5,000, and from the mid Holocene to recent, we looked at these glacial lake records for our paleoclimatic study. So what we have seen that all along the length of the Indus, this is the longitudinal profile, at four places the river has been blocked in the late Quaternary times, giving rise to these big massive lacustrine deposits. Now, I'll come to the paleoclimate bit of it a little later, but before that, I would like to say that in these records, in these paleolake records, we also see evidences of tectonic activity in form of the soft sediment deformation structures. They are convolute structures, sand dikes, their folds, falls, flame structures, many, the morphology of them is it's very wide. And along with these, we also see unpaired and tilt terraces. There is a basin asymmetry that we see. Deep gorges, I've already talked about it. There are slope failures where the slopes are blanketed with debris and paleolandslides. So all these, they hint towards a tectonic activity in this region during the Quaternary times. So all these Paleolithic sections, wherever these are crosses, we have seen deformation structures at several levels. Sometimes there are multiple levels, sometimes there are just one. These are horizontal structures. These are bound by horizontal layers up and down, and they are just in one layer. And to the lateral extent also, you can trace them. So no doubt of them being seismites. When you put everything together, so these seismites, these layers were dated by OSL and AMS, whatever suited where. So we see that in the Indus Valley, they concentrate more at about 10,000 to 9,000 years before present, and during 6,000 years before present. Yeah, or lateral extension. We did the same thing in the other valleys also, which are the tributaries, the Shyok and the Tanze valleys. There we are seeing them differently as 27,000, 23, 21, several dates we've got from different areas. And then in the southern part, the Tethin Himalayas or the Spiti Valley, again, some workers have worked, and then they have shown that, 11,000 and 6,000 were the areas where there was tectonic activity has been recorded in the sedimentary record. As of today, when we see the seismotectonic map of the region, so this is the region which is hardly showing any earthquake, or they are showing very shallow to intermediate, focus earthquakes with magnitudes very less, 3.4, 3.5 to 6.9 as per the recent studies. And what has happened is this is the Karakoram fault, and here we can see that there has been several researchers have given a slip rate in the Karakoram zone. So this area is active. We see earthquake centers here in the seismotectonic map, and towards the south of the study area, which is the main central thrust, and the Korek Chango fault, which is the South Tibetan decollement area and all. But this is not so much seismically as prone as we can say. But in the past, we've already seen seismites at 10,000 and 6,000 years before present. So it's that, and in the records which are after Holocene, because they were the late sediment records. In that, we could not see seismites because they were cores or short trenches that we took sediments from. So just I leave you here with the question that the past has some record, but this present does not show any. But the future could have some, and this is more because at this portion, this is the Himalayan arc. At this portion, wherever the blue is the Trans-Himalaya, here what is happening, the convergence of the Indian and the Tibetan plate is oblique convergence. So what is happening because of this direction of the oblique convergence? So there is this Ladakh batholith, which is acting as a backdrop, backstop. It's stopping the Indian molassic sediments, and then, back thrusting is taking place in several series. So because of this, there has been tectonic activity in the Indus-Sucha zone area. And we have some very good papers from Sinclair and Kumar from Wadi Institute that the Stoke thrust, which is an expression of the Indus-Sucha zone in this area, so it has been active. So this could be the cause of activity. And then if you see it in this figure, in this photograph, the beautiful, the quaternary sediments, they are like just overriding the suture zone. This is just on the suture zone. So you can see the gouge-like things. So this is the batholith, and there it's just riding in. So this shows the, and this activity has been dated by Sinclair to 45,000 years before present. So, things are going on in this area as far as tectonics is concerned. Now I come to the second part, which are the paleo outburst events, because we're talking about the natural hazards. So what has this part of the world in store for us? We have records of paleo outburst events, and I'll give you an example from a small catchment of the river Indus. This is what called the Gya River. So this river is a left bank tributary of Indus. And then if you see all these records here, the damming events here, and we have a set of terraces. So I'll take you to this area. What is happening here? This is the longitudinal profile of the river, and here we see that at 3 points there is a sudden drop. At Nick point 1, there is a drop of 120 meters, then again 30 meters and 30 meters. Yeah. So what has happened is, and if we see the cross valley profiles, the upper reach is V-shaped valley, the lower reach is V-shaped valley, but the middle reach here is a wide valley where there are terraces, where it's a U-shaped valley. So now, as the mountains here have glaciers and they have pro-glacial lakes. So whenever there is a flooding, it just dams the river at a narrow point. And then what happens is that, a back flooding starts, and a paleo lake is formed for some point of time. Yeah. And then what we did was we recorded 3 such in the sedimentary record. We saw such lacustrine deposits, which we could say were because of the outburst events, and then later the back flooding or the paleo lake damming, that paleo lake formation that was there, which existed. We have some radiocarbon dates, and these are natural dam rates, over us. The dates took us to 19,000, 21,000, 13,000, and 4,000. And before this, in this area, 3 glacial stages have been recorded by Orr et al. So the oldest is the Lato stage, that is very old, but I'll come to the Shriul stage, that is 25,000 to 15,000, and the Kiambu stage, that is 3 to 0.2 kilo years. So basically what we observed in our results was that the damming phases are happening when there is a transition of the climate. Yeah. So at 21 to 19, we know that the LGM, that cold, dry LGM is leading to a warming or a deglaciation phase. So, the outburst is happening. The second phase is 13,000 K. We know that increased temperature during the Alroid and interstadial makes much meltwater and increased energy condition for this outburst too. And the third stage, again, we know that there is an abrupt transition from the warm mid-Holocene period to the cold, wet late Holocene. So wherever a transition in the climatic conditions is seen, so these places like Ladakh would react. So during this phase of transition in climate, there has to be some it would come in the surface as outburst events or something like this. Now we come to the third part, what is happening in the ridges. Okay, so we saw the main valley, we saw a small system of the valley, and now we see what is happening in the range itself. So Ladakh range, it has lots of river basins, to be exact is 41,128. and 6 of them are more than 300 square kilometers. We went to this largest basins, Leh and Changla, and did some studies there. There are several glacial lakes in this area. So now just imagine we're standing at about 5,000 meters. We hardly see any glacier, no ice patch. This is summer, and the lake is like a small pool in the side. And for sampling, we take these JCBs, and then we take every centimeter as a sample for our paleoclimatic record. And what we see, the obstacle here is the permafrost. Now, just after 80 centimeters, you get this black frozen soil, and then you cannot dig. Even the machines, the bulldozers, they cannot dig here. So and this permafrost, what we see when we are doing field work in several areas, what we see that the active layer, which was at 30 centimeters or at 70 centimeters, it's already melted during this time. So it's no longer a permafrost. So maybe in the present warming scenarios, this is a major threat to permafrost also of the region. So much work has to be done here on the permafrost mapping and permafrost, especially the permafrost, because we lose the cryosphere very, very soon. As in the Ladakh range, we've already lost many of the glaciers, only the ice patches remain. So what we did here was took a lot of lakes, both on the northern phase and the southern phase of the Ladakh range, and we used it for our paleoclimatic studies. I recently gave one lecture in Dr. Peter Cliff's monsoon series. In that, I've given details about how we did these studies, climatic studies. So I'll just give a brief outline about it, because then it would be a repeat. So what we did was, because we were applying a suite of chemical, physical, and biological proxies for it, so this is just one data that I'm showing here. So we could construct from 4,000 years to 200 years before present. We could do a sub-century scale data, and we could also tell that in the climatic zones, which forcing was dominant. Yeah, whether it was the northern forcing or it was the ISM. So and then small things like, the presence of diademosphenia and charcoal in the sediments near 2,000 years. It told us about the human presence. The stressed diatoms told us about, the ecological stresses, ecology of the lake, and so on. So basically what I'm trying to show here, and in the other slide, that in the paleo lake data, that the paleoclimatic data that we have collected so far or published so far, right from this is from 17,000 to 6,000. So we have a complete record after the LGM of the data. So, and remember modeling in the paleo lakes, what is happening, that the biotic proxy, the diatoms and all, we don't see that. So we did some end member modeling and mineral magnetism, and total organic content, as you can see, is very, very less values, and then delta 13C, and we also calculated the paleo precipitation. So with all this, what happened is the picture that we get is that after the LGM, the westerlies have been dominant in the area. This is also, the paper by Dodge 2013. They have said about the glacial stages, different glacial stages at this point of time. And then, just as the Holocene is coming, the warming is coming, we have this ISM phase, until 6,000, again, we have the westerly phase. So we could see which forcing is dominant right from LGM to the present, taking the paleo lake data and the glacial lake data over it. Now, what is happening is, as I said, now, the climate has its own forcings and the tectonics is taking place. So when I just put everything, not everything, but something of the Indus Valley together, so what I see is like there has been tectonic activities, the red lines. So, and you see many of the lakes are formed after the tectonic activity. Many of them are getting breached after the tectonic tectonic activity, so they are tectonically dammed lakes also, but some are not tectonically dammed lakes. There is the exogenic forcing there. So exogenic forcing, the climate forcing, is also acting as for the formations of the lake in this area, and also the endogenic forcing. So now, as the present scenario, because we need to understand what is going on today. So this is the average. The green one is the average precipitation in the last century, and we see that the pink one is the June, July, August, September rainfall. That is ISM rainfall, and the blue is the westerly. So the contribution has been all throughout. It's not like, one is stopping, or one is only one is there. It was believed that total moisture, about 2/3 was coming from the westerlies and 1/3 from the ISM, by a few years before. But what we see today in the papers that come from the isotopes, composition of water, lately these papers, they say now in Ladakh it's 26% from the Mediterranean only, and rest is coming from the ISM source. And when we see the record, we see that the March, April, May temperatures are rising. The June, July, August temperatures are a slight rise, but the January, February temperatures are rising. That means it's less of winters and more of this, melting. So that is why the Ladakh range as of today has no active glacier, as we can say. So the tectonic activity and the changing climate, it has given rise to paleo lakes, glacial lakes, outburst event, and of course a threat on permafrost in the Ladakh region. Now I'll just take 10 more minutes and just show you example of the Shyok River Valley. Shyok River Valley is again a tributary of the Indus, of the main channel, and it is a big river in itself, as you can see. Yeah. So Shyok River, as I said, it comes from here, and what we observed was, the sediments all along the river bed. In the eastern part, there is a big lake called the Pangong Tso Lake. Yeah, this lake is it's a valley lake. It has 5 sills, separated sills. It is 165 kilometers, and the international boundary between India and China, it straddles over this lake. So this is the part with India. So what we saw was the western side of the Pangong Tso, and all these points were the points of observation. So in the Shyok Valley, what we were surprised to see that there has been this, some kind of a paleo shoreline that we were seeing in the Pangong side. We were seeing such kind of, distinct line, and wherever there were the inner parts, or the streams that are joining the Shyok, we see them the deposit very well and very nicely, and this is the same lacustrine, fasci, clays, and silty sands. Yeah, the lake deposits all throughout. So right from Paleo Lake 1, PL1 to PL16, you can see here, that's the Pangong Tso. So deposits like this are spread over all along the valley, 40 meters, 10 meters, so many, everywhere. As you go down, because you're descending down on the longitudinal profile, so you see it in the same contour level until Batalik, where it is just massive debris flow is there, and the lake sediments are like just blocked. After that, we do not see the sediments at all. So what does it mean? Does that mean that the Pangong Tso, it had a 6th basin, and it was so huge in the western side? That is what we wanted to see. We got some 45 chronologies from the OSL chronologies and radiocarbon chronologies. All the circles are the radiocarbon chronologies, and the OSL chronologies are the boxes here on the fluvial sections. on the fluvial lacustrine sections, the yellow ones, on the lacustrine sections, and some glacial in the Nubra Valley, of course, and then the glacio-fluvial sections. So all these are there, and what we were surprised to see was that the entire lacustrine sections, they were from 10,000 to 6,000 years, to 4 or 3,000 years before present, this. So they grouped well here. And then, so in the Tangze Valley, that is the connect of the Pangong so to the main Shyok River, we see lacustrine phase, and these are big, massive, 40 meters at Shachikul, Tangze, many sections, Durburg. And then in the Shyok itself, the Farka Topo, the Khalsar sections, they show us these dates, meaning to say that, there was extent of the Pangong so was extending into the Tangze, into the Shyok River via the Tangze River at some point of time after the Holocene. And this does collaborate well with the oxygen O18 isotopic record of the Gulia, where the strong monsoon and strong monsoon peaks are seen, and the precipitation is seen in this area. So there has been a lake in this region, which was a connect to the Pangong. So so this entire region is 185 kilometers. And the Pangong Tso itself today is 165 kilometers, and in the east also we see some kind of a shrinking in the satellite data. So what was happening in the Indus? We had dams, paleo lakes in different parts, but in the tributaries, in one of the tributary, there was a massive lake, a valley lake was there existing. And in a smaller catchments, the outburst or the paleo dams were being formed. This is all late Quaternary. So possibly the valleys that we see as today, they must have looked like this some 10,000 years back. And this is no exaggeration. This is no exaggeration because I take you to a real-time example of this. I take you to the Humza River Valley in Pakistan, which in 2010 was, this river was blocked by this massive landslide. The entire hill comes down and the lake starts forming. The lake waters, they rise at a level of 15 feet per day because this is March, April, melting is taking place. All the glaciers are there. A lot of melt water into the lake. So this is Humza landslide dam in Pakistan. So the entire hill slope comes down. Reasons could be many. And the lake starts forming, the water starts rising, everything is coming underwater. The entire villages that are near the river, they are, flooded with water. The rescue operations are there. The people are coming towards the higher levels. And rescue operations, Pakistan Army is there. The famous Karakoram highway is underwater, so a lot of loss of life and property. The rescue operations, where there was a river, there is a lake today, and lot of there was a lot of loss of life there. And then there was an additional danger, and this is happening in just few months time, a year's time. Additional danger was that what if the water pressure that's building up upstream, if it just gives way, because this is just loose debris, what would happen to the villages, the river downstream? What would be the hazard or assessment of the disaster was needed? So they did an outlet in that lake in which the water overflow was, excess water was overflowing to save it from it. So there are many hazards that are related to high mountain hydrometeorological conditions. And because of this rising temperature, changing weather, abrupt weather scenarios, so spring floods, in some catchments, they are causing big losses, not only in the Himalaya, but even we hear of, like, this was Hunza in Pakistan, from the Tinshan, from the Pamir, we do hear about these outbursts or the lakes, and then lake outbursts, which destroy the infrastructure and the human lives. So when we see it in the Ladakh perspective, what we see that there has been shifts in the major forces crossings in the past years. And today we see a very greener Ladakh. Ladakh is supposed to be a very arid cold desert, but now we see greening there. And perhaps because of the paucity of records in this section, especially 30,000 to 17,000 because of the LGM and all. So there has not been much data, but as data comes, or we get sections, because here, as the physical weathering is so intense, everything gets washed away and it is concealed by the debris. So in no point of time. So because it's a very dynamic system, so we really do not have much records from here. And we see that the lake records, they are forming, some are forming after the tectonic activity, some are breaching after the tectonic activity or the seismic activity in the region. So both endogenic and endogenic forcings here have shaped the geomorphology of the area. And if we again come to the third pole dynamics now, you all must have seen this scientific assessment report of the third pole environment, which was published by the UNEP last year. It also says it is a compilation of researchers from several groups of scientists and researchers all over the area. So a general warming and wetting climate has been, is seen, and water bodies have shown increase in variations. Like in the Ladakh range, we see more lakes now. Otherwise, they were all frozen throughout the year. It was only a snow cover that we used to see. Then the third pole has been turning green. And then the projections that were made in this reports are really very scary, like 2050, 2100. What would happen is that because of these consequences, we will face more, of such risky events, which would be caused by the warmer and wetter climate that is predicted in the future. So with these words, this was just an assessment, a scenario that I wanted to show you what is happening in the Ladakh sector. And this wasn't possible without the help of the students, teams, funding agencies, colleagues, collaborators, laboratory facilities everywhere. So I would like to acknowledge all of them, and I would like to acknowledge you, Professor May, for giving me a chance to be here and talk to you. Any questions? It would be really nice to have an interaction. Thank you.